Okay, so we've been working our way through understanding Snell's law and taking this formula bit by bit, dissecting it to try to understand what each piece of it means. And in the last video, which would have been number 2 in this series, we talked about the variable n and how that means refractive index and what the refractive index was. Okay, now that we know what n is, what is sine of angle I and sine of angle R? Well, if you're not up on your trigonometry, you're probably wondering, what is sine? So let's go over that first. What is sine? Sine is a function of a right triangle. A right triangle is a triangle where one of the three angles is a 90-degree angle, meaning it's a square angle. In a right triangle, we label the sides as adjacent, opposite, or hypotenuse. The long side is the hypotenuse. Okay, the side that's across from the angle that we're talking about is called the opposite side, and the side that's next to it is the adjacent. The sine of a particular angle in a right triangle is the measurement of the opposite side over the hypotenuse side. So in this triangle, we are looking at this particular 30-degree angle because we've already labeled opposite and adjacent. So we know the sine of this particular 30-degree angle will be the measure of the opposite over the measure of the hypotenuse. So the measure of the opposite is going to be 2 feet. The measure of the hypotenuse is going to be 4 feet. And if we just do the math, we can simplify that down to say the sine of this 30-degree angle is 1/2 or 0.5. That's how you find the sine of an angle. And something that tends to confuse people is the fact that all 30-degree angles in a right triangle are going to have a sine of 1/2, regardless of how big this triangle or small this triangle is. People sometimes get confused about that, but if you type in sine of 30 degrees into a calculator, you're going to get the answer 0.5. And it's very simple. Think of two circles or two pies. They're different sizes, one's bigger and one's smaller, but half of the bigger one and half of the smaller one are not equal, but they're still both a half. It works the same way with sines of an angle in a right triangle. Okay, now what if you need to kind of work backwards, so to speak? What if you need to find that angle right there? You don't know what the measure of that angle is, but you do know the sine of that angle is 1/2. You know the opposite side and you know the hypotenuse. So you know the sine of it is 1/2, but you want to know what the angle itself is. Well, you use something called the arc sine, which is 1 over the sine, the reciprocal of the sine. Now these are 3 different ways to denote arc sine, to write it. All 3 are correct. You'll generally see it, the middle way, sine to the -1, because that's the way it is on most calculators. But I want you to be able to recognize it regardless of the way it's written here. Sometimes you will see it 1 over sine. Sometimes you will see it written out arc sine. Okay, so all 3 of these are the same thing. They all mean arc sine, the reciprocal of the sine. So the arc sine of 1/2 is 30 degrees. How did I know that? I punch it into my calculator. Yeah, that's pretty much the way. Okay, so back to our formula. The only thing that we really don't know at this point is what is angle I and what is angle R. Even though we know one is the angle of incidence and one is the angle of refraction, because we know what I and R are, let's just take a look at what angles exactly we're talking about. Okay, here's our picture of our light ray traveling along, hitting a surface. And it is a surface of another medium, a transparent medium, because it continues on through that medium, but it has a different density, a different refractive index, and we can see that because the light ray is bent. Now let's just draw the path that it would have taken had it not been refracted, had it not hit this other surface and been refracted. Now we're going to do just what we did when we were working with reflected rays. We're going to draw an imaginary line. This purple dashed line is an imaginary line perpendicular to the surface. And we're going to call that the normal. And angle I, the incident angle, is the angle formed between the incident ray and the normal. I'm going to repeat that. The incident angle is the angle formed between the incident ray, the ray coming in, and the normal that we drew. Okay, so the sign of angle I in this equation, I'll just look at these next few slides. I'm not really going to explain this too much because you don't really need to know it in depth, and I think it's self-explanatory. So here's how we find the sign of angle I. And angle R in our equation is the angle formed between the normal that we drew and the refracted ray. The normal that we drew and the refracted ray. Okay, now we understand everything in this formula for Snell's law. I'm going to do another video to show you how to use this formula and how to find the refractive index. But one more thing before I end this video, I want to talk about how do we know which way the ray is going to bend once it's refracted. And we do know that. We know that because it depends on the refractive indices of these two materials. Okay? If N sub I, that's the refractive index of the material that the incident ray is in, the ray coming in, if that is less than the refractive index N sub R, then the ray is going to bend towards the normal when it refracts. Okay? If the incident ray is in a denser material, N sub I has a greater refractive index than N sub R. It's going from a denser material to a less dense material. Then that refracted ray is going to bend away from the normal. Okay, I'm going to say that whole thing again in a different way because I like to repeat myself. The denser medium will have the higher refractive index. Okay. If the light ray is going from a denser medium with a higher refractive index to a less dense medium with a lower refractive index, the light ray will refract away from the normal. And what that really means is, I find a better way to say it than away from the normal, not in between the normal and the path that that light ray would have taken had it gone straight and not been refracted. Okay? And it follows that if the light ray is going from a less dense medium to a more dense, a denser medium, that light ray is going to refract towards the normal, or in between the path it would have taken had it not been bent and refracted, and the normal, in between those two, towards the normal. Okay, now that we've basically gone through all the parts of this formula in order to understand Snell's law, maybe next video we can start to use it on some real life practical problems and understand it a little bit better. But for now, thanks for watching.